So, hello everybody. I'm here with Aliénor Lahlou, and she's from the sustainability team. That is the team we are starting to know today. And I'm very happy to be with you, Aliénor. And so I would ask you to present yourself.
Hello. After studying in a French engineering school, ESPCI, I did a master thesis in machine learning and joined the team of Sony for an internship where I worked on plant segmentation that David presented. And then we wanted to continue in a PhD with a topic a bit different. So we contacted many laboratories and met with the ENS chemistry team of Ludovic Julien and Thomas Lesaut, who work on fluorescence. And we decided to do a PhD thesis of early stage research on plant diagnosis using fluorescence.
Okay, thank you. So you are working on plant diagnosis, and is it a side project in CSL, or is it linked to what we have just saw outside, to the robot development in the lab?
Okay, so the project will be a bit far away, but the long-term objective is that one day we can put the device we prepare on the robot. The way it would work is that the robot sends light on the plants. Then the plant emits fluorescence, and collecting this information, the robot will compare it to a database and be able to do a status analysis. For example, say this plant needs water, or this plant is under pest attack, or this plant needs fertilizer. And maybe the robot will be able to act directly or tell the farmer that it's time to act.
So good. Great. And so, if I understood well, you collect the plant fluorescence to get a diagnosis of the status of the plant. Is it correct? Yeah. Where does it come from?
Okay, so it's actually a natural process. And if we want to understand, we have to look at the root process that allows plants to grow, which is photosynthesis. So photosynthesis allows the plant to capture gas, CO2, and takes electrons from the water to fuel the photosynthetic chain and make sugars using the energy of light. So what happens is that inside the leaf, you have chloroplasts, and in the chloroplasts you have what is called thylakoids, which are filled with pigments. So these pigments, they absorb the light energy and transfer it to a reaction center where the photosynthesis happens, which the light energy is converted into chemical energy. However, the antenna cannot control how much energy they get. So if it's a morning, not too much sunlight, they capture a light energy that matches the capacity of photosynthesis. But when it's later in the day, at noon, you have full sunlight, and they receive too much energy. So to avoid damage, they release this energy through two processes, either heat or fluorescence. So that's really interesting for us because we can measure the light of fluorescence.
Oh, okay.
And so what happens really is that we look into the waste of photosynthesis. But if you think about it, you can learn a lot from looking into a trash can. Let's say I look into your trash and I find vegetable,
and also pizza, of course.
Then I can say that you're healthy. But if I can only find tissues and med boxes, not a lot of food, then I will know that you are sick. So there's a lot we can learn from waste.
Oh, this is really amazing. And has fluorescence already been used to probe the health status of a plant?
Yes, it has been used. It's not new. It has been used for a lot of years. And there are several methods. What we want to introduce is a new method to look at it.
Okay.
So for now, what we do is look at the photosynthesis under several when the chain is under several stresses and compare the levels and extract information. For example, how many photons are converted into photosynthesis and how many are lost. But what we want to look at is the dynamic response of the photosynthesis, like when you excite it at different frequencies, how it responds. And what we want to do is probe specific steps of the photosynthetic step to have more understanding of what's happening. So what are the advantages of it? that we're doing a dynamic analysis, so we target specific steps, and also it has a high signal-to-noise ratio due to the frequency analysis method. And it will be easy to implement on fields and can be used outdoors. And we want to rely on machine learning to do classification of the signatures and understanding. So from this, we will be able to get diagnosis analysis, but we can also select strains, like to see how they behave in certain circumstances. And maybe what we want to do is optimize growth condition. In other words, minimize the amount of waste you find in the trash to be sure that it's completed into sugars.
Okay.
So to do this, introduce a new method is not that easy. So the first step was to build an instrument. Then to be sure that our instrument was trustworthy, so reproduce the experiments from the literature. And then with partners with the same sample, compare the same experiment at the same time.
Yeah.
And finally publish a paper to show, present our instrument to the community. And finally, we can work on the idea. So for the first year of my PhD, I worked on building the instrument, and at Sony and ENS, we always start from scratch. So we built the microscope from zero. It consists in several light sources that we inject into the setup, and we can collect light on the sample and collect the fluorescence and use either a camera or a photon counter to acquire data. So these are some images that we acquire. We can look at plants, and we can also look at algae. And actually, we will focus on algae because it is the typical organism to study photosynthesis.
Okay.
And here, for example, you can see a video of our, okay, it doesn't work. Of our algae trapped in a microscopic trap, so the size of a hair, and we can look at them one by one.
Wow.
And what we wanted to do is really only light one at the same time, at a time. So we worked on the setup, and since we made it from scratch, it's really easy to adapt. So what we did here is replace our manual platform with an automated one. So with 3D printing and motors and an Arduino, we can control our setup and look at each trap one after the other.
Yes. And I mean, what are the advantages of building a new setup by yourself?
Okay, so the first is you can modify it, and another advantage is that you can completely control it and make it automatic. So we use Python for automation, and it allows to reduce human error and increase reproducibility of our experiments. Also, we put all our data in a database, and everything is stored with all the experimental parameters. So let's say we do our experiments, and then in 5 months we have an idea that we want to test. We can reuse all the previous material. And actually, it was not easy to find a way to implement this. It seems that it's not so common, so I had to adapt a platform for machine learning to my laboratory experiments.
Okay.
Nice. Then the next step was to reproduce results from the literature. I will not go into details, but we showed them to the results. These are 3 types of experiments, and we showed them to by experts in biophysics, and they said that they were completely relevant and reproduced correctly the literature. And then with our colleagues, we took the same sample of algae, and the same day did the same experiment, and we managed to find very similar results, which was saying you can now try to work on the instrument for other questions. So if we wanted to publish, we had to find a new question that we could tackle with our instrument. And what we decided to do was to study the distribution of a population. Usually, when we study samples, we look at the mean of the response. But here, what we wanted to do is to isolate each individual algae and get their own response, and then look at how the dispersion of the response was. And the next step will then be to work on the method.
The method. Yeah. Okay. So it seems to me you are very enthusiastic about this project. And so I would ask you how it was working on the project.
It's really interesting because it's very pluridisciplinary. There's optics, computing, biology, and it allows me to interact with a lot of people. And I had a lot of luck to fall on Sony and ENS because they already have a lot of knowledge and also a lot of contacts.
Yeah.
So I get to meet a lot of
Yeah.
people.
Okay. And how is your experience of the lab?
Um, it's quite funny. So I was more used to work with computer science, and working with biology materials, it's quite hard because it's hard to anticipate how it behaves, and it's hard to cultivate, and there's a lot of, um, of unexpected conditions that happen. But it allows you also to find unexpected results. It's a really unpredictable system, and we find things that we didn't expect,
Okay.
thanks to the instrument.
Great. So thank you, Aliénor, and thank you for giving us such a deep insight on the topic. And so this was our last interview of the day, and I just want to thank everybody who was following our live stream program during these 3 days. And I will just say that at 15 we will have another moment to stay together. And so I thank you, and I will wait for you at 15. Bye.